Go. Okay, so how would you graph something that's moving at a constant speed in the same direction? You can also respond in chat, or you can, like, show me with your hands. So everybody doesn't like say it out loud. Linear graph. Okay, linear graph. Horizontal line. Linear graph. It is linear, yes, but it's going to be horizontal, right? Since velocity is not changing. Oops, that's not what we want. Yeah. So it's going to be horizontal line. Since line is linear, it's going to be like that, right? So now I'm making a claim that the area under this line will represent displacement. Again, we're going to be using displacement instead of distance, and in a little while it'll become clear why we use different terms. Okay, so what I'm saying is this area is equal to displacement. Now, some of you may be familiar, remember the formula for like rate from middle school, or like the rate of change or something. So let's try to relate to that. So if I want to find the area, I have to multiply, it's a rectangle, right? So I can multiply base times height. So here it doesn't matter which one is base, which one is height. But we're gonna label a few things so we can relate to the variables. So these are variables, even though like we're fixing the position, the numbers could be of all kinds. So we're using a little bit of algebra. So if I want to find the area, I'm gonna draw the shape here. It's gonna be base times height. So that means displacement is equal to V times T final minus T initial. So why is it T final minus T initial? Because we take this interval of time, and from that we subtract this interval of time. Does that make sense? The difference between T final and T initial. So Ti stands for T initial, Tf stands for T final. It's the same thing as when you use a stopwatch, right? You start, let's say you start observing something, it's ticking, and at a certain point you saw something else, you notice 45 seconds, and then that something else ended at 90 seconds. How long did that second process take? If it started 45, ended at 90 seconds, how long did it take?
45.
45. So we just find the difference. Okay. So how would the motion, let's say now you are in a Formula One race car, right? On the start, you're about to start the race. And how would the graph look like once you stepped on the gas? So Formula One, the start is given, you step on the gas, how would the graph look like? Horizontal line, you'll not go anywhere. Positive slope, linear, positive slope, linear. All right. So here we go, like that. So what we do is, again, we make the same claim that the area, it could be exponential, right? But the thing is, I mean, in real life, probably it is exponential. But in real life, this is not real life. This is virtual life. In physics classroom, we introduce a simpler kind of motion. And you should relate to, again, remember I told you that it's emotional science. So remember your emotions or feelings when you're in the car and the car is accelerating suddenly or like stopping suddenly, right? You won't feel comfortable. It's much more comfortable if you know that it accelerates at the same rate, so that the feeling of the force will be kind of constant. So you can kind of adjust to it, and then you don't have to readjust all the time. So we don't like accelerating, like, I mean, it could be exciting, but usually people don't like to experience this every day of their lives. So we want to get the like steady acceleration. So this graph will look like linear. So now we're gonna again mark these things. This will be V final. This will be V initial and final velocities. And again, T initial and T final. Now, to find the area, we need to find, the shape is obviously a triangle, right? So I don't have to explain that. The area of a triangle is 1/2 base times height. So we're going to use exactly the same equation and then just change a little bit of the variable. So displacement is equal to 1/2. Now here I'm going to introduce something that will be clear just one step later, okay? Sometimes I will tell you, trust me on this, but it'll be, you don't have to trust me this much, you have to trust me just this much, okay? Because then in the next step, I will show you the reason for this statement. But overall, I will tell you this, do not trust me. I may make mistakes. I may say wrong things. I may have a wrong explanation. So what you do, you have to have your brain on all the time, actively analyzing what I'm saying. So I don't want you to take everything I say as like teacher said so. Okay, I'm not authority to impose my values on you. I am in position to explain the reasoning, and it's up to you to process it and accept it or not accept it. Some of you will not accept it. I mean, I don't know. Maybe you will, but later. So try to understand the reasoning behind it. And I'm going to explain that just a little bit. So here I'm going to put V initial plus V final times T final minus T initial. So you may say, why is it not V final minus V initial? Because that's going to be like, say, the height of the triangle, right? But you will see why it becomes clear just in a little bit. So we're going to keep it like that. Let's try another example. So let's say now you are driving again, but you're on a service road which enters the highway. On the service road, let's say the speed limit is 30 miles per hour. On a highway, you have to reach, say, 60 miles per hour to join the traffic safely, right? And you have limited amount of time to do that. And within that time, you should go from 30 to 60. So if we were to plot the graph of your motion from the moment you start accelerating to the moment, you're on the highway, how would that graph look like? Okay, I appreciate if you can respond in the chat, or you can also like wave your hands. Will it look the same as this one, or there will be some difference? Steeper. Remember, you are already in motion, right? So that should be on the graph. It would not start at 0, so it would start at 30 in this example, right? Now we're not going to put the numbers, we're going to put the variables. So I'm going to draw this. And let's say we forgot to observe you right away, and then we kind of observed you a little bit later. So then we can actually look at this part of the graph. And again, the area here will represent displacement. So question to all of you. Again, it may be a silly question, maybe you all know already. What kind of shape is that? All right. Trapezoid, right? Trapezoid. Okay, what kind of trapezoid is that? Now that's a little bit more like a specific question. The reason I ask you the kind of trapezoid, because we have to look at it, right, and find out the basis of this trapezoid. So it's kind of, it's a right trapezoid, but it's like on its side, right? So then if you put it on its base, then it will like look like a trapezoid from a perspective like that. So, and formula for the trapezoid area. is 1/2 base 1 plus base 2 times h, right? Is it correct? Yes. All right. So easy stuff. So we're gonna again relate to that and draw the displacement equation. V final T final minus T initial. All right. So far so good. Is anybody lost? Okay. So easy stuff. What we do now is we want to relate triangle to trapezoid. And I'm gonna make a bold claim that those are the same shape actually. Triangle is a trapezoid. Can we say that? Have you ever imagined the trapezoid looking like a triangle? No? Yes, no? Okay, let's try. So this class again is about imagination. We're gonna try to imagine. So we're gonna make this trapezoid enormously large. Okay? We're gonna make the second base, so this base I'm pointing at, really tall. And then we're gonna move away from this trapezoid really far. Okay, you have to use your imagination, like in this, obviously in the virtual world, we can do it like this, right? So zooming out, expanding the trapezoid, making this side real tall, making this side really big, but forgetting to enlarge this side. So if you go really far from this, this will diminish to almost a point, right? Does it make sense? So now all of a sudden we're looking at this weird trapezoid, we can't see one of the bases. It's almost zero, so it will look like this. Make sense? So then the formula has to be consistent. The formula for the displacement or the area has to be consistent. So, and then there you go. You see the same formula here and here. So they describe the same thing. Now I'm going to take one more step and say that trapezoid is the same thing as a rectangle. Can we say that? You can nod, you can do this, you can type. Okay, it is, right? If you have two bases equal, then that's your rectangle. So technically this equation is also the same as this equation. And we didn't invent anything new, actually. We established one simple fact, which all of you know, I'm kind of reiterating. All of these are two-dimensional shapes. And in general, in two-dimensional shapes, you multiply base times height, in general, right? And that's what we did. Now, let's introduce any questions. Remember, I told you, be active, ask questions. If you don't ask questions, you guys are boring. No questions, everything is crystal clear? Seriously?
I still don't understand why we're adding the V1 plus VF, and then we're subtracting TF minus.
Okay. So the reason we're adding is that the same thing as I was trying to explain, these shapes are basically the same thing. Which means when we write the formula for the area, we should get the same thing, the same equation.
I get that they're the same thing, but like, why not just do like, for the triangle, why can't we just do like TF minus TI, and then VF minus V1?
Mm-hmm. If you do this, then you lose the information about one of the velocities. What I mean by that is, if I say that area of a trapezoid is average of the bases times height, and I say area of a triangle is what's it called? What's the number called? Midpoint, right? Midpoint. So this is a formula for the midpoint along the y-axis, isn't it? So if I take this shape and cut it in the middle and place this triangle. Let me actually do that. If I take this shape and cut it in the middle and take this triangle and put it here, right? I'll end up with the average for the height times the base. Does it make sense?
It makes more sense, yeah.
Okay.
Thank
So
you.
if there was a minus, we wouldn't be able to do that because we would be lacking understanding why we're doing midpoint.
Okay, but like if we're bringing that small triangle to that part, right?
Mm-hmm.
But then isn't it like VF minus V1 then? To find
No,
like
no, because this was the midpoint. And what's the formula for the midpoint? It's average, isn't it? Like
yeah.
y, y1 plus y2 divided by 2, right?
Oh, okay, wait, that makes sense then.
Make
Okay,
sense?
thank you. Yeah.
Okay, I'm gonna leave it like this. So since the video, you can always go back. I'm not gonna erase the notes. Okay, are there any more questions? Okay, now we're gonna introduce a word that, again, you're all familiar with, but we have to bring a more like scientific meaning to it, physics to it. So the word is acceleration. Acceleration. Long time ago, the gas pedal was called accelerator. Step on the accelerator. And then later, people shortened it to the gas pedal and then gas, just gas, and that's it. And then now we confuse gas, which is like gas made of molecules, right? And expand it. Gas for gasoline and gas for the gas pedal. Everything is gas. So acceleration. Acceleration. It's made of two parts. Air, and I guess it was a longer word, but basically it's air plus celerity. Celerity. So celerity means speed, air means additional, so we can write additional speed. Additional speed. So it literally means you add on to the speed, right? But it's a very simple or oversimplified meaning. And we're going to use a more general meaning of the word. Acceleration. Acceleration could be when you're going faster, when you're going slower, or when you're even turning. Like if you're on a bicycle, you're making a turn, you are accelerating. And a definition for acceleration is acceleration equals change in velocity over change in time. Now remember, we're using lowercase v for the velocity, right? Sometimes it may look like uppercase, but it's lowercase. If it's uppercase, I'm going to draw it like this. Okay, so this will, you will know it's uppercase. So this is the lowercase. So that means, go away. That means v final minus v initial over t final minus t initial. Now, excuse me. People are lazy. Smart people are even more lazy. So we're going to be smart lazy, meaning that we don't want to write t final minus t initial all the time. Again, the reason for that, you can always reset the stopwatch to 0. You can always say, well, t initial is 0, so I don't have to write, always state that explicitly. And we can, instead this we can just write v final minus v initial delta t. So for a little while, we'll keep using delta t, and a little bit later, we will just discard delta altogether because we're lazy, okay? Who wants to write delta t when you can just write t? And in general sense, algebra or any kind of like mathematical discipline, mathematics, they want to write expressions in the most concise manner, right? So that's the reasoning. But motivation, I'm telling you, is being lazy. Okay, so this is our acceleration. And what we want to do is to derive two useful expressions. And before we go there, I have another question. I'm kind of answered my question already, but maybe you missed that. What do we call a quantity where, well, like if you had two values and then divide the sum by 2? What do we call that?
The midpoint.
The midpoint, okay. What else? Feel free to respond in the chat.
The average.
Average, mean, average, midpoint. Midpoint will be on the graph, right? If it's a graph, but if it's like a, let's see what we have. We have time. All right, good. So I should be able to finish it. So we're gonna call it average or mean. Now remember this. Whenever someone says like, you know, mean things or the person is mean, it literally means it's an average person. Okay, average. You don't want to be mean, you want to be special, right? Special. So what we're gonna do, we're gonna write a general equation, right? And general again means mean, average, but it works all the time. And that's how it's gonna look like. Total displacement equals to average velocity times delta t. This equation will always be useful. It's always correct. So I'm going to box it. And here I'm going to mention this. One of the classes asked if you're going to use reference tables. No, do not use reference tables. Okay, forget about them. For the probably couple of months, we won't be using them. Maybe sooner, maybe later, but I don't know. But I want you to take a piece of paper, a nice piece of paper that will last a little longer, and start collecting, assembling all those formulas. So this is one of them, okay? And these two are auxiliary formulas, meaning that they're useful, but they're not always useful, okay? And then in some problems, you can apply this right away. You get the answer. In some problems, you have to apply more like this formula. So write down those formulas, and those formulas will be then on a piece of paper. You create this formula because you write them with your hands. You will own them eventually. And to own them, you're gonna have to put them, every night you're gonna start praying now. If you have not been praying, you're gonna start praying. Every night before you go to sleep, you're gonna look at the formula sheet and just stare at the formulas. You don't have to think about them, but part of your brain will be thinking about them because you're looking at them, right? Your thoughts may be completely off, but part of your brain will be thinking about. And then when you sleep, you put them under your pillow. Hopefully by osmosis, they will go, into your brain, okay? And if we do it gradually, I guarantee that by the time you accumulate all the formulas, you will know at least 80% of them by heart. So if I call you at 2 o'clock in the morning and ask you what's like formula for uniformly accelerated motion, you will have it, okay? So, and then later we're gonna use reference table because reference table is something, it's useful, but it's not always useful, okay? So I don't want you to get used to something that's not always useful. All right, next slide. Next slide, where's the next slide? Give me the next slide. Why is not giving me next slide? Okay, next slide. Zoom is acting up today. Okay, so we will try to derive two special equations. Special meaning that they only apply in specific cases, but they are nevertheless useful because you will solve lots of problems with special circumstances, special kind of cases, right? Again, I emphasize this is not real life physics because real life physics is much, much more complicated. First, we have to know how to handle elementary level kind of physics, okay? So we have two equations. One equation is D equals 1/2 V initial plus V final times delta t. I don't want to write t final minus t initial. And we have acceleration equals to v final minus v initial over delta t. You can think of it as a system of two equations, v1. And what we want to do is we want to modify them. Let me move them up a little bit. So that we end up with two different equations. And this is again called algebra. One of the equations should be looking like a function. F stands for the function here of the variables, initial velocity, acceleration, time. See, I'm already writing just time instead of delta t. And actually, let me write delta t for a little bit. Yeah. And then the second function should include initial velocity, final velocity, acceleration, but no delta t. Okay, so usually in class I would say derive these two equations. And let me look at the times. I don't know how much time. Did you guys have gym today? Yes? Zoom gym? Gym over Zoom? So we are on period 2 now, right? 10, 15, 11, 10, 11, 10. Okay, so let's try to do it together. And we're gonna, and then what you're gonna do, your homework exercise will be to try to do it on your own, deriving the two equations. And that's when you will own these equations, when you derive them on your own on a blank piece of paper. So for the first one, we don't want to see v final, which means we need to eliminate v final from the acceleration formula. So I can write that like this. I know in math classes you write like multiply both sides by delta t, blah, blah, blah. I'm gonna just write it like this. V final equals V initial plus a delta t. So I solved it for the V final. I solved this equation. Let me point at that. For the V final. So these are related, okay? So now I'm going to take this expression and plug it into the top equation. So I'm going to draw that here. Let me use different color. So now it's going to go not quite there, but like let me be more specific over here. Okay, so let's see what happens. D equals 1/2 V initial plus, instead of V final, we write V initial plus a delta t close delta t. So all of you know distributive property. I don't have to teach you this. So if you distribute this, you will end up with D equals V initial delta t plus 1/2 a delta t squared. I'm done. But if you don't see how we get there, that's when your homework exercise will be useful. When you're going to derive, if you do it like multiple steps, the way you learn in school with math, distribute 1/2, combine like terms, distribute delta t, blah, 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 and finally you will get that. Okay, so this is a useful formula, but it's not always useful. It still has to go to your formula sheet, onto your formula sheet, okay? So now we're going to try to derive another one in which we do not have time, right? Over here, no time. So we need to solve acceleration equation for delta t. So I'm going to write it over here. Over here. Okay, so marker. So acceleration is equal to that. So which means delta t equals V final minus V initial over A. So what I did, I just swapped the delta A with delta T with A. Okay, and now delta T in the expression here will be replaced with this. So let me draw that connection also. So this will go over here. All right, so D equals 1/2 V initial plus V final times V final minus V initial over A. Okay, now we can leave it like this, but it's not really concise, right? Do we see a familiar identity here? Algebraic identity? Does anybody see that? Does it have a name? No name? Difference of the squares, yes. Okay, difference of the squares. So this will become difference of the squares. So V final squared minus V initial squared over 2A. Again, I may have skipped some steps, mathematical steps that you're used to. This is where you're gonna do your homework and then figure out how we get this. Difference of the squares of this two, right? And 2 and A are in denominator. That's how I did it. So I didn't break any rules. All right, let's block this one. Again, this formula goes onto your formula sheet. Okay, so let me look at my, where's that page? Oh, I need to look at the page. Now, what I wrote in the morning statement, was it correct about schedule? I asked if something's wrong to comment. I got one comment. So tomorrow we have A1 day, right? Again. So you guys will have double, right?
We don't see each other tomorrow.
Yeah, we don't have class together
Oh,
until
you don't have.
Wednesday.
Oh man, this sucks. Oh man. So I will see another class for double, right? No, I don't see another class for double. Oh, this sucks again. Okay. I'll see a different class for the single, and then when will I see you guys for double?
Wednesday.
On Wednesday. So on Wednesday we have double. Okay, so right. So I'll update that for the Wednesday and Thursday then. If anything is wrong, just let me know right away so I don't put the wrong schedule there. Okay, any questions about today's lecture? I'm gonna actually stop recording.